make sure that you know all the concepts in your syllabus. Okay, question number 2. Let's look at this now. On the Argand diagram, sketch the locus of the points representing z. Now, think about it. Modulus of z equals 9 and argument of z equals pi over 2, between pi over 2 and pi. Now, how can we do this? We've done this before. We've done this before in other recent papers as well. What does this mean? Modulus of z equals 9. What is this locus going to be? It's a circle. Modulus of z can be thought of as z minus 0, right? It's a circle with center 0. And radius 9. Okay, so that's one thing. So there's azan going on here. I have a few seconds break and then we'll see. Can you guys see my screen again? Yes. Now I can see it on my other device as well. Let me see if it is still lagging. Achha, so if you're sending me any message, make sure that you send it to the host account. Send it to the host account or just send it to everyone. That will be safer. If you're sending a direct message, a private message, send it to the host account, okay? The one that has the video on. Otherwise, I'll not be able to see your message. Okay, chale. So we were given the complex number z satisfies this equation. Modulus of z is equal to 9. That means we have a circle with center at origin and radius 9. Now the circle should be drawn with a compass. It should pass through these points 9, minus 9, 9, minus 9. Achha. Now they're saying another condition is the argument of z is between pi over 2 and pi. So what we can do for that is we can make a line like this from the origin, 90 degrees, pi over 2 radians. That's going to look like this, pi over 2 radians. This will be one line, right? And then another line, which is pi radian line. What is that going to look like? That line will be like this. Now, you can be anywhere between these two. What that means is this is the region that satisfies both of those inequalities. Now, this is one way of doing this, but in the recent marking schemes, the way they actually show this is rather than shading that part of the curve, what they do is they just show the part that is valid. So they don't have anything else showing there. And they just do something like this. So that's what you should do ideally. This is the region that this is the curve, this is the arc that satisfies both of those conditions. Its modulus is 9, its distance from origin is 9 units, and the angle is between pi over 2 and pi. This angle is pi over 2, and this angle is pi. So we'll make a line like, make a curve like this. So yes, you should erase the rest of the circle. This will be locus of the points representing z. Okay. In this case, since we don't have an area as such, it's just all the points on this arc. So it's a good idea to just not shade any region. Instead of that, just show this arc and erase everything else. Okay. Now they're saying on the same diagram, sketch the locus of z conjugate plus 3. What is this going to be now? Z conjugate plus 3. Z conjugate plus 3. What is z conjugate? When we find conjugate of something, what happens is the imaginary part flips. And we have seen questions like this in recent past papers as well, where they ask you for the geometric effect of taking a conjugate of a complex number. What is that geometric effect? Reflection in the line x-axis. Why does that happen? Because the imaginary part flips. So if we were just thinking about z conjugate, that would look like this. That will be an arc like this. This would be z conjugate. It will be reflection of that in the x-axis. Okay. However, we also have a plus 3 there. We also have a plus 3 there. What do we do about that? Plus 3 means in the real part, we are adding 3. What happens because of that now? When we add 3 to the real part, the horizontal axis represents the real part. What will happen would be this graph is going to move 3 units to the right side. Okay? The real part is going to increase by 3 units. So what happens is this curve is going to shift to the right by 3 units. So now it will be starting from -6 here. Erase the rest of it. It will be starting from -6 here and going up to this point, which is 3 and -9. So this is what it looks like now. You can draw this roughly like this. And you say this is the locus of z conjugate plus 3. Make sense to everyone? Isn't it a change in the imaginary part? Do we have iota with it? This is just 3, right? 3 is a real number. 3 is a real number. Okay, no problems with this. Let's move on now. So plus 3, that's the real part. We are going to add 3 to the real part, right? So that means it moves to the right. It moves to the right. And yes, you should be making this arc using a compass. Use a compass for making this arc. Put your compass needle at 3 here, open it 9 units, and make an arc like this. Okay. Achha, now it's given that z is equal to 3 plus lambda iota divided by lambda plus 2 iota, where lambda is the real constant. Find the value of lambda for which argument of z is equal to this. Okay, so we find the argument of this complex number z, and we put that equal to pi over 4, and that will give us the value for lambda. How do you find the argument of this number? We would have to simplify this first, right? We have to simplify this. Let's simplify this first, and then we will try to find the argument. We can say 3 plus lambda iota divided by lambda plus 2 iota. We can multiply and divide by the conjugate of the denominator. So multiply and divide by lambda minus 2 iota. Now, the numerator, what's that going to be? 3 plus lambda iota into lambda minus 2 iota. In the denominator, it's a plus b into a minus b. So that becomes lambda squared minus 2 iota whole squared. Okay. Now 3 into lambda, that's 3 lambda, 3 into minus 2 iota, that is minus 6 iota, plus lambda squared iota minus 2 lambda iota squared. Okay, that's the numerator. What about the denominator? In the denominator, we've got lambda squared minus 4 iota squared. Let's simplify this. In the numerator, we have 3 lambda minus 6 iota plus lambda squared iota minus 2 lambda iota squared. That is going to become plus 2 lambda. In the denominator, we have lambda squared plus 4. Now, write the real part separate, imaginary part separate. 3 lambda plus 2 lambda, that will become 5. So we can say 5 over lambda square plus 4. That's the real part. And then the imaginary part, the terms that have iota in them, we could say they are minus 6 plus lambda squared divided by lambda squared plus 4 times iota. This is what z simplifies to if we separate the real part and the imaginary part. Is that okay? Any issues with this? 5 lambda होएगा? 5 lambda, yeah, in the numerator. ठीक है, अच्छा. Now that we have simplified this, they have told us the argument of z is pi over 4. Now, which quadrant is this in? It is in the first quadrant. Keep that in mind. It's in the first quadrant, such that this angle is pi over 4. Now, if with angle pi over 4, real parts and imaginary parts, they're equal to each other, right? But you can just input in the formula as well. What's the argument going to be? It's in the first quadrant, so whatever is the basic angle, that's the argument. So we can say argument of z, that must equal tan inverse of imaginary part divided by the real part. Okay, that will be a bit too complicated fraction. Let me just write it down anyway. Minus 6 plus lambda squared divided by lambda squared plus 4 whole divided by 5 lambda divided by lambda squared plus 4. Okay, so what I've done is I've divided the imaginary part with the real part. Now this must equal the argument that they gave us, that's pi over 4. So this should equal pi over 4. Now what happens is lambda square plus 4, lambda square plus 4, they get cancelled. Tan inverse goes to the other side, becomes tan pi over 4. On the left side, we're just left with minus 6 plus lambda squared over 5 lambda. On the right side, it becomes tan pi over 4. Tan pi over 4, put this on your calculator, that will be 1. So we have 1 equal to minus 6 plus lambda squared over 5 lambda. And again, we get a quadratic equation, lambda squared minus 6, that is equal to 5 lambda. Lambda squared minus 5 lambda minus 6 is equal to 0. Now, how do we solve this quadratic? There was another part to this as well. Where did that disappear? Okay. Lambda squared minus 5 lambda minus 6. We have to factorize this. Lambda squared, we can say there are two factors, lambda 6 and 1, right? So minus 6 and plus 1. Lambda minus 6 and lambda plus 1. These will be the two factors that we get from this. And lambda is either equal to 6 or lambda is equal to -1. These are two values of lambda that we're getting. Now the question said find the value of lambda. That's a singular. So that means there has to be only one answer. We're getting multiple answers. That means one of them is not going to be possible. One of them is not going to be possible, right? Now, how do we ignore one of them? We know the angle is supposed to be acute, so we are in the first quadrant. We are in the first quadrant. In the first quadrant, that means the real part should be positive and the imaginary part should be positive. So we can just check if any of them is giving us maybe a negative real part or a negative imaginary part. Let's check for that. This is lambda squared, this is lambda squared. If we put -1, however, what happens is the imaginary part here becomes negative. The real part also becomes negative with -1, right? Both parts become negative. That means it can no longer be in the first quadrant, then it will go in the third quadrant if the real part is negative and the imaginary part is also negative. So for that reason, we would have to ignore lambda equal to -1. We'll say this is not possible, and the only possible value of lambda, therefore, is lambda equal to 6. Whenever you get multiple answers, always go back to the question statement and see if all of them are going to be possible or not. Okay, so in this case, -1 was not possible. Any issues with this? Any problems, anyone? Lambda is wavelength. अच्छा इसका second part जो है ना, that is missing from here. Let me copy that. When lambda has the value found in part 5a, find the exact value of modulus of z, making our method clear. Now, once we have this value for lambda, this was the z value that we were getting, right? After simplification, we could just use that, input lambda equal to 6 in this, and then find modulus from this. Input lambda equal to 6. What do you get? 5 into 6 divided by 6 square plus 4 plus minus 6 plus 6 squared divided by 6 square plus 4 iota. What does this simplify to? Can anyone tell me? 5 times 6 is 30. 30 over 40. That will be 3 over 4, right? Please confirm this. This is 30 over 40 as well. 3 over 4 minus 3 over 4 iota plus 3 over 4 iota. right? Yeah, that looks okay. What about the modulus of z now? Do not write down the answer directly. Show the step. 3 over 4 whole squared plus 3 over 4 whole squared, and then take square root of that. And that will give it the modulus. What's the value for modulus that you're getting? What's the modulus value? What's the modulus value? Has anyone done this? 0.75 squared plus 0.75 squared. Square root of this, and that is, do they want an exact answer? Yes. Achha, since they want an exact answer, we actually should show further working as well. We'll say this is 9 over 16 plus 9 over 16, and that becomes 18 over 16. And then we could say 18 can be written as 3 under root 2 divided by 4. Yeah, that's what we were getting, right? 3 under 2 over 4. And that's your final answer. Whenever they ask you for exact values, make sure to do it step by step. Do not skip any working in that case. Let's start with this one. Question number 5 from this paper. It says the shaded region on the Argand diagram shows points representing complex numbers z defined by two inequalities. The shaded region is bounded by a circle and a line parallel to the imaginary axis. So there's a vertical line and there's the circle. The shaded region is to the right of this vertical line and inside the circle, to the right of this vertical line and inside the circle. The boundaries are included. That means the inequalities, they will have the equal to sign in them as well, right? Less than equal to, greater than equal to. Find two inequalities in terms of z that define this shaded region. Now, first of all, let's start with this vertical line. What's the equation of this vertical line? Vertical lines are of this form: x equal to some constant. Now, on the x-axis, we've got the real axis. On the horizontal axis, we've got real numbers. How do we write this equation then? We could say the real part of z, that is equal to 2. That is what this equation represents. Okay. Now, since we have to be to the right side of this, what is the inequality going to be? We will say this is real part of z greater than or equal to 2. That is the inequality that we would get. Greater than or equal to. Okay. That's the first inequality that we've got. The shaded region is also inside the circle. We can write down the equation of the circle, right? What's the equation of the circle going to be? The standard form for the equation of a circle on an Argand diagram looks like this: z minus center that equals radius. That's the standard form for equation of a circle on an Argand diagram. Now, what's the equation of the circle going to be? The center is here. Center's coordinates are 1 and minus 2. So what's that complex number going to be? This is 1 and minus 2. We can write it like this: z minus 1 minus 2 iota. This is the center. Then what about the radius? From the center, you can see 1, 2, 3, 4. It's 4 units, the circumference. So the radius is equal to 4. That's the equation of the circle. Okay, you can simplify this as well if you want. If you simplify this, that gives you z minus 1 plus 2 iota. Modulus of that is equal to 4. That is the equation of the circle. All points on the circumference. Oh yeah, I'm sorry that. So I took this as 4. This is 2 units from 2 to 4. The scale is 1 box. 2 boxes represent 1 unit. So the radius is 2. Equation of the circle is this, right? With 2 on the right side. Radius is 2. Now this is the equation of the circle. Since the shaded part is inside the circle, so what we do for that is we have less than or equal to sign, and the inequality is going to be modulus of z minus 1 plus 2 iota. That is less than or equal to 2. Right? So radius is 2 units in this case. 2 boxes represent 1 unit. That's the second inequality. Okay, that's your final answer. Make sense? That's the first part. Let's look at the next part now. In the next part, they say calculate the least value of argument of z for points in this region. Real part of z greater than 2, will that be wrong? They explicitly mention that the boundaries of the region are included in the shaded region. So that would not be completely correct if you do not put equal to sign with the inequality. However, sometimes they allow this as well. It will depend on the marking scheme, but it's risky. Sometimes you will get a mark for this, sometimes you won't get a mark for this. So you should write greater than equal to in this case. Yeah, depending on the mood of the examiner, sometimes they will allow it, sometimes they won't. Okay, all right. Yeah, you can look at the marking scheme whether it's allowed or not. Camera is not on. Okay, I'm sorry, I did not see that. Okay. Achha, calculate the least value of argument of z for points in this region. Least value of argument is z. Now, how do you find least value of argument? Argument is measured from origin, right? So from origin, let me make a line. From origin, we could have lines like this, right? Where is the argument going to be least? Is this argument least? It will be some negative value, but we can make it more negative, right? We can make it more negative and more negative, and we can keep going down until we pass through this point at the bottom, right? This is where the argument is going to be the least. This is where the argument is going to be the least. We need to figure out this angle somehow. This is the angle that we want to find out. Is it not the greatest? We measure argument from this positive real axis. When we go in the upwards direction, angle is positive. If we go downwards, angle is negative, right? So when we go in this direction like this, we want the greatest negative value, right? We want greatest negative value. So the greater the negative value will be, overall, the argument will be smaller, because if this was the argument, let's say this angle was minus 0.2, then here it might be minus 0.9, let's say. Minus 0.9 is smaller than minus 0.2, right? So on negative side, bigger magnitudes are smaller numbers. Is that okay? But how far further on to this side can we go? We have to be in the shaded region, right? This is the lowest point in the shaded region. We can't go any further than that. We have to stay inside the shaded region. Makes sense, right? Okay. Now the problem is, how do you find this angle? How do you find this angle? That's the question now. So what we know is the center. It's not passing through the center. It's not diameter. We cannot assume that this length is 4 units. It looks like it's passing close to the center, but it's not actually passing through exactly to the center. But we do know the x coordinate of this point. This point has an x coordinate of 2. That is one thing that we do know. Can we find the y coordinate of this point somehow? Can we find the y coordinate? One fairly quick way of doing this could be use the equation of circle from the coordinate geometry. Equation of circle form from coordinate geometry. What was that? X minus a whole squared plus y minus b whole squared equals r squared. Write down the equation in this form. Center's coordinates are 1 and minus 2. So this will become x minus 1 whole squared plus y plus 2 whole squared equals r squared. Radius is 2, so that's 2 squared. That's the equation of the circle. Now, if we know x is equal to 2 at this point, we can find the corresponding y coordinate by just inputting x equal to 2 in this equation. Let's input x equal to 2. And that gives us 2 minus 1 whole squared plus y plus 2 whole squared equals 4. Find the value of y from this. Y plus 2 whole squared equals 3. Take square root on both sides. Y plus 2 equals plus minus square root of 3. And you'll get two values of y from this. They do not want an exact answer. You could also find an exact answer if they wanted, but they've not required that. You could write decimals as well. You'll get one positive value for y, no, both negative values. You'll get one negative value here, another negative value here. You will use the one that is smaller, right? That's the point that we're looking for. What are the two y values? What are the two y values that we're getting? One is under root 3 minus 2, and the other is minus under root 3 minus 2. We are looking for the smaller one, right? This is more negative. So you could say this is the y coordinate of that point. You can use decimals as well. What's the decimal equivalent of this? Minus 3.73205. Okay, that's the y coordinate now. So we know this point is minus 3.73205. That's the y coordinate of this point. Now, once we know the y coordinate, we can find that angle now using this right angle triangle. We have this right angle triangle. In this right angle triangle now, we know that the base is 2 units and the height is 3.73205. Right? Use tan and that will give you that angle. Let's call this angle theta. We can find that. Tan of theta equals opposite, which is 3.73205 divided by 2. And that will give you a value for theta. You can see what that turns out to be. What do you get from this? In complex numbers, generally we use radians, so it's a good idea to use radians here. Although in this case, since we're not really using this angle anywhere else after this, degrees may also be acceptable. But you should make it a habit. If the question does not specify anything, use radians. Okay, otherwise you can end up making careless mistakes sometimes. Okay, that will give you the result. You can see what that is. This is 1.0788 rounded off to three significant figures, and that will be 1.08. That's the least possible value for the argument of z. This is what we were looking for. So this idea where we use equation of circle from coordinate geometry in problems like these, this is used a lot in such questions. Whenever you're looking for the point of intersection of some line with the circle, it often helps to use this equation of circle formed from coordinate geometry. There may be another way of figuring this out as well using circle properties, but that will be harder. That will be harder. So this will be least argument at the end will be negative 1.08. Yes, that's the final result that we get. Negative 1.08. Angle theta is 1.08, but we have to go in this direction. So the final answer is going to be negative 1.08. Yes. Okay. Make sense to everyone? All right, acha. Let me try to reduce some clutter from here. That was question number 5. We're done with that. Okay. Why won't we choose the point at the top? Let's suppose we take this point. Let me take your suggestion. So you're saying take this point on top. The argument at this point would be this number, right? The argument that we have just found, it turned out to be minus 1.08. So this number is minus 1.08. If I take that top point, that argument would be some other value, right? So let's say that's negative 0.2 because it will be a smaller magnitude, right? Now this is negative 0.2. This is negative 1.08. Which one of them is the smaller number? Which one of them is the smaller number? Is negative 0.2 smaller or negative 1.08 smaller? Negative 1.08 is smaller. So this is going to be the least argument. If they had asked you for the greatest argument, in that case, we would take the top point. That will be the greatest argument. This point will give you the greatest possible value of the argument. Is that okay? Won't we go anti-clockwise? The interval that we use for argument is from negative pi to pi. That's the convention that we've got. So in the first and second quadrants, we go from the positive direction. In the third and fourth quadrants, we go in the negative direction. That's the convention. So we follow that. So that will also be negative, but from this direction. Okay. Number 3, let's have a look at this. It says find the complex numbers z for which z plus 5 iota divided by z minus 5 is real and modulus of z is equal to square root of 17. This is a complex number. They're saying this is real. And modulus of z is square root of 17. Square root of 17, give your answer in the form x plus y iota. Now, how do we think about this? When they say something is real, what does that mean? There's no imaginary part, right? The imaginary part is going to be 0. The real part will have some value, but the imaginary part, that is going to be 0. This thing has an imaginary part equal to 0. Now, how do we use this information that's given? Let's write that down. We can start like this. Since we want the final answer to be in this form, we can say let z equals x plus y iota. Now, why am I doing this? So we can isolate the real part and the imaginary part from z. Since they have said this fraction is real, we can simplify this fraction, and then once we have the imaginary part from this, we can put that imaginary part equal to 0. So that's why what I've done is I've written z equal to x plus y iota, because now if we look at this fraction, we can simplify this as z plus 5 iota divided by z minus 5. We can replace z with x plus y iota, so it becomes x plus y iota plus 5 iota divided by x plus y iota minus 5. Okay, this is what we end up getting. Now, how do we simplify this fraction? When we have a complex number in the numerator and another complex number in the denominator, how do we simplify that fraction? What's the process that we've got for that? We multiply and divide by the conjugate of the denominator, right? Now, first of all, before we do that, we can write the real parts together and imaginary parts together. In the numerator, the real part is x. Imaginary parts are both of these terms. So in the numerator, it's already arranged properly. In the denominator, however, x minus 5 is the real part and y iota is the imaginary part. So when we multiply and divide by conjugate, what is the conjugate going to be? Conjugate of the denominator, real part remains the same. That means x minus 5 remains the same. Change the sign of the imaginary part, that's minus y iota. Both multiply and divide by this number. Multiply and divide by the conjugate of the denominator. Now we can simplify this. What do we get in the numerator? X into x, that is x squared. X into minus 5, that will be minus 5x. X into minus y iota, that will be x minus xy iota. Then multiply y iota with all of those terms. That gives you plus xy iota minus 5y iota and then minus y squared iota squared. Then multiply 5 iota with all of those terms and that will give you 5x iota minus 25 iota minus 5y iota squared. Now you have to be careful in this working. A lot of careless errors happen in this working. So you have to be uh, careful that you're not making those mistakes. In the denominator, what do we have in the denominator now? Let's write that as well. In the denominator, this is a plus b into a minus b. We can write that as, that's also fine, Umesh, you can do that. Y plus 5 whole iota. You can write it like this, but then multiplication is going to become a bit more complicated, right? If you multiply this thing with this, multiplication becomes a bit more complicated. So it's better to leave it in simplified form. Okay. Acha, what about the denominator? In the denominator, we can think of it like this. This is a plus b iota into a minus b iota. So that's x plus y into x minus y. That becomes x squared minus x squared minus y squared, or a squared minus b squared. So in the denominator, we get x minus 5 whole squared minus y iota whole squared. Okay. Now we just have to simplify this. Minus xy iota and plus xy iota in the denominator, they get cancelled. Is there anything else that also gets cancelled? Not really. Okay, let's simplify the numerator now. Simplify the numerator. X squared minus 5x minus 5y iota minus y squared iota squared. What does this become? Iota squared is minus 1, right? So this will become plus y squared. And then plus 5x iota minus 25 iota. Iota squared again, that becomes negative 1, right? So that's plus 5y. Okay? Let's simplify the denominator as well. X minus 5 whole squared. What's that? X squared minus 10x plus 25 minus y squared iota squared. This is what the denominator is. Now let's simplify this a bit further. In the numerator, what's the real part? Let's separate the real terms. X squared minus 5x plus y squared minus, or in fact, plus 5y. These are all the real terms. And then the terms that have iota in them, they are imaginary. Minus 5y iota plus 5x iota minus 25 iota. These are the terms that are imaginary in the numerator. What about the denominator now? The denominator simplifies to x squared minus 10x plus 25 plus y squared. So when we simplify this fraction, this is what we end up getting eventually. Okay, this is what we end up getting eventually. Now they said, this fraction is real. That means its imaginary part is supposed to be 0. So all we have to do is put the imaginary part of this complex number equal to 0. So we can split the real part and the imaginary part, right? If I were to write it as two separate fractions, I could say this is the real part. And then what about the imaginary part? We could split the fraction, right? We could split it into two parts like this, where this is the real part and this is the imaginary part. We could split it like this. Okay. Now they are saying the imaginary part is 0. So all we have to do is This thing, we put this equal to 0. So we ignore the real part. We don't really need that anywhere. We just have to put this thing equal to 0. Okay? So what do we get from that? In the numerator, we have minus 5y plus 5x minus 25 whole times iota. The imaginary part is this, right? Divided by x squared minus 10x plus 25 plus y squared. Put this equal to 0. Now, when you put this equal to 0, what happens to the denominator? That will go to the other side and get eliminated. 0 into anything is 0. What are we left with? Just the numerator. Iota will also get eliminated, right? So what we essentially end up getting is that minus 5y plus 5x minus 25, that must be equal to 0. We can divide the whole thing by 5 to simplify this further, and that gives us minus 5 plus x minus 5 equal to 0, or you can say y is equal to x minus 5. This is one equation that we're getting in terms of x and y. Is this okay to everyone? Right? The question says this fraction is real. If it is real, what that means is if we were to simplify this, its imaginary part will be equal to 0. Imaginary part of this fraction, that is going to be 0. Okay? Imaginary part is equal to 0. So all we are doing is we are saying, let's simplify this fraction. Let's simplify this fraction. How do we do that? We replace z with x plus y iota because z is a complex number which is of the form x plus y iota. We write it like this, and then we just multiply and divide by the conjugate like we normally do for fractions. What's the conjugate of the denominator? The real part in the denominator is x minus 5, so that remains as it is. Imaginary part, we change the sign for that, so it becomes minus y iota. We multiply by this and also divide by this, and then it's just simplification. At this point then, if I have, for instance, x plus y iota divided by 2, if I have something like this, or in fact, let me write some numbers there. If I had 3 plus 5 iota divided by 2, I can break it into two parts. I can write the real part separately, 3 over 2, and the imaginary part separately, 5 over 2 iota. That's exactly what I'm doing here as well. We are saying these are all real terms. Let's write them separately with this denominator. And then all the terms, sorry, these are the real terms, we write them separately with the denominator. And the rest of them are the imaginary terms, we write them separately, just like we wrote it in this case. And then, since the question said it's a real number, the imaginary part therefore should be equal to 0. So we just put the imaginary part equal to 0 for that reason, because if it is real, the imaginary part should not exist. So this whole thing must be equal to 0. So that's why we're just inputting that equal to 0. Is that okay now? Okay. Achha, that's a good question, and it's an important clarification that I think I should give here as well. Some of you might be thinking of it like this: z plus 5 iota divided by z minus 5. You could say somebody might think of it like this, that just multiply and divide this fraction by the conjugate of the denominator without doing the substitution z equals x plus y iota. Now, what's the problem with that? Now, first of all, what's the conjugate going to be in this case? Yeah, since you've asked this question, what do you think is the conjugate of denominator? What's the conjugate of denominator in this case? There's no iota visible in this case, but even if, let's assume we did have some iota term in the denominator as well. Now, this is not this fraction in the question, but let's suppose we had z minus 3 iota in the denominator. Let's suppose we had it. Let's suppose we had iota as well. Then would it make sense to multiply and divide by z plus 3 iota, even if there was iota there? Would this step make sense? We multiply and divide by conjugate like this? Multiplying, dividing by z plus 3 iota? Will it make sense or not? It would not make sense still. Why? Because z plus 3 iota is not the conjugate of z minus 3 iota, because z itself is a complex number. Now, since z itself is a complex number, there is an iota term inside z as well. It will have a real part, it will have an imaginary part. So there's an iota inside z as well. So when you talk about conjugate, the imaginary part of z, that should also say change sign. To be able to do that, it's necessary that we first break it down into x plus y iota so we can change the sign of this y iota as well. Otherwise, this cannot be said to be the conjugate of this number. That will not be correct. Is that okay? So we have to first split everything to real and imaginary parts. Then we can find conjugates after that. Okay? Achha, let's move on now. So now that we have this equation, there are two unknowns, one equation. That's not enough. We need another piece of information. For that, they have given us that modulus of z is equal to square root of 17. If modulus of z is equal to square root of 17, we can get another equation from that. We can say modulus of z is equal to square root of 17. What is modulus given by? X squared plus y squared. Square root of that is equal to square root of 17. Square both sides and you get another equation, which is x squared plus y squared equals 17. Now we've got two equations, solve them simultaneously, and that will give you the values of x and y. Now from the first equation, we've got y equals x minus 5. You can input that here and that will become x squared plus x minus 5 whole squared, that equals 17. Simplify this and that will give you x squared plus x squared minus 10x plus 25 minus 17 equal to 0, which simplifies further to 2x squared minus 10x plus 8 equal to 0. You can see if you can factorize this. 2x squared, can we factorize this? 8 and 2 will work, right? Minus 8x minus 2x plus 8 equal to 0. We get two factors from this. 2x minus 2, that's one factor, and the other factor is x minus 4. So there are two possible values of x that we get, x equals 1 or x equals 4. These are the two values of x that we're getting. Now we input them back in the other equation. Input them back here. You put x equal to 1 here, and then you input x equal to 4 here. When you input x equal to 1, you get 1 minus 5, which is minus 4. When you input x equals 4, you get 4 minus 5, which is minus 1. So what is the complex number z then? Z was x plus y iota. One possible value of z could be 1 minus 4 iota, or z could be 4 minus iota. These are the two possible values of z that we end up getting from this. Okay? Again, I think already had a complex number question before. Let's have a look at this now. They are saying it is given that z1 is equal to this, z2 is equal to this, and w is equal to this. These are three complex numbers written in the form r e raised to power iota theta. That's the form that these numbers are given in. We need to state the values of wz1 and wz2, giving our answer in the form r e raised to power iota theta, where argument is supposed to be between minus pi and pi. Achha, now for both of them, we can either use normal multiplication, like we multiply any two things, or if you remember those properties, which you should remember, when two complex numbers are multiplied, what happens to their modulus? When two complex numbers are multiplied, what happens to the modulus? They get multiplied, and the arguments, they get added. Right? These properties, you need to remember them. Modulus of u into v, that is the same as modulus of u into modulus of v. So when two complex numbers are multiplied, their modulus are also multiplied. And the arguments, they are added. They are summed up together. And when two complex numbers are divided, their moduli are divided and the arguments are subtracted. And these are rules that you need to remember. Properties of complex numbers when two complex numbers are multiplied or divided. We could use these properties as well there or do normal multiplication. It's your choice what you want to do there. In this case, multiplying normally is also not going to be very long. If I just do it directly, WZ1, what is that? W is 2e raised to power pi over 2 iota. And then Z1 is 3e raised to power pi over 4 iota. Now when 2 and 3 get multiplied, they give us 6, right? Now e raised to power something and e raised to power something, when two things are multiplying and the bases are the same, what happens to the powers? Powers get added. So it's going to be 6e raised to power pi over 2 iota plus pi over 4 iota. Put this in your calculator and see what that simplifies to. Pi over 2 plus pi over 4. What does that give you? It will be 3 pi over 4, right? So this gives you 3 pi over 4 iota. This is WZ1. Then they're asking you for WZ2. What about that? W is 2e raised to power pi over 2 iota. We need to multiply this by Z2, which is 3 over 2. E raised to power pi over 6 iota. Again, 2 into 3 over 2, what does that give you? 2 into 3 over 2, that is 3. Powers get added, so it becomes pi over 2 iota plus pi over 6 iota. What about that? 4 pi over 6, which will be 2 pi over 3, right? 2 pi over 3 iota. These are two things that we were looking for in the first part, right? That's pretty straightforward. That's simple algebra. Now they're saying on a sketch of an organ diagram with origin O, show the points A, B, C, and D representing the complex numbers Z1, Z2, WZ1, WZ2 respectively. Achha, let's make an organ diagram now. Whenever you draw an organ diagram, use the same scale on both axes. Okay. So you will measure this using a ruler ideally. In this case, it's still not that much of a problem, but when you're drawing locus, in those cases, you need to always make sure that you use the same scale on both axes. So if I have 1 unit here, then it will be the same distance on the y-axis as well that we say is 1 unit. So 1, 2, 3, -1, -2, -3. Similarly, on the left side, -1, -2, -3. This is imaginary axis. It's necessary to label the axes. This is real axis. Achha, where is Z1 going to be? Z1 is 3e raised to power pi over 4 iota. Where is this point going to be? 3e raised to power pi over 4 iota. Where is this going to be? How do you plot that? 3 is the modulus, right? 3 is the modulus. And pi over 4 is the argument. Pi over 4 means 45 degrees, right? So the point Z1 is supposed to be such that its distance from the origin is 3 units. Distance from origin is 3 units. And it's at an angle of pi over 4. Pi over 4 is 45 degrees. That becomes a gradient of 1. Okay? We talk about this when we do complex numbers. 45-degree lines mean they should be like this, such that they pass through 1, 1, 2, 2, 3, 3. That's the line at which the point z1 is going to be. So it's going to be somewhere on this line, such that its distance from the origin is 3 units. You can say this is pi over 4, the angle, and this point is z1, such that the distance from origin is 3 units. That's your first point. Acha, what about z2 now? Z2 has a modulus of 3 over 2. That means 1.5. It's half of the modulus of z1. So whatever the distance is of z1 from the origin, z2 should be half of that distance. And what's the angle for that? Pi over 6. Pi over 6 means 30 degrees. Now 30 degrees should be slightly less than 45, right? So you can make something like this. That's not necessarily going to be accurate, but you can roughly make something like this. You can say this is Z2. It has a slightly smaller angle as compared to pi over 4. And the distance from origin for this, that is 1.5 units. Let me mark these slightly smaller. This distance is 1.5. That's Z2. Okay. You can use protector for the argument. You can do that, but it's not necessary as such. Okay, they would not deduct marks for this. 45 degrees angles, they have to be accurate. But apart from 45, all they care about is if the angle is greater than 45, it should be above this. If it's less than 45, it should be below this. And that should be fine. It doesn't have to be very accurate, no. You can use the protector if you want to, but it's not required. Okay. In locus questions, I would recommend that you still do it because that will help you with the calculation part in the next part. Calculations become easier if your diagram is accurate. Achha, what about WZ1 now? WZ1, that was this, right? 6 units. So it is going to be twice the distance as compared to Z1 from the origin. Modulus is 6. And what about the angle? Angle is 3 pi over 4. 3 pi over 4, what's that in degrees? 3 pi over 4 into 180 over pi. This is 135 degrees. So it's going to be in the second quadrant like this. It's going to be in the second quadrant like this. 6 units away, so you can mark that somewhere here. This is WZ1, such that its distance from the origin is 6 units. Okay? And this angle is 3 pi over 4. And then finally, WZ2, what about that? That's distance of 3 units from origin, so half of this. And the angle is 2 pi over 3. 2 pi over 3 in degrees is 120 degrees. So 120 degrees, where is that going to be? It's going to be above this line, right? The other line is 135. So 120 is going to be slightly before that, somewhere around here. This will be WZ2. So as long as the positions of Z1, Z2, WZ1, WZ2 are relatively correct, that will be acceptable. Okay? Makes sense, right? We move on. Okay. Achha. Now it says state the geometric effects of multiplying Z1 and Z2 by W. Now, geometrically, how is the diagram changing? How are the points changing? So Z1, when you multiply that by W, when you multiply Z1 by W, what happens is it goes there. And the second thing that happens is when Z2 is multiplied, it also goes there like this. Now, what are the geometrical effects? That means in terms of transformations, what kind of transformations are happening? Can you figure that out? What transformations are happening? One is very clear. This is ongoing on here. We have a 1 minute break. Think about it. Then we'll assume. Okay, let's resume. So in the first part, we found WZ1, WZ2, and then we sketched them. Now they're saying state the geometric effects of multiplying Z1 and Z2 by W. Now, how are Z1 and Z2 changing after multiplication with W? Now, what's happening to Z1? It was here. It went there to WZ1. And then Z2 was here. It went to WZ2 here. So one is very obvious. One is very obvious that there's some kind of rotation happening, right? What rotation is happening? W had an argument of pi over 2. W had an argument of pi over 2. So in both the arguments, we ended up having to add pi over 2, right? We were adding pi over 2 to the arguments of Z1 and Z2, because of which there is a rotation. In which direction? Anti-clockwise. There's the anti-clockwise rotation by pi over 2 radians. Okay? So that's one thing that's happening. When we multiply by W, since the arguments increase by pi over 2, we can say there's an anti-clockwise rotation. There's an anti-clockwise rotation by pi over 2. What's the center of rotation? What's the center of rotation? About the origin, right? So in such problems, in complex numbers, whenever you are asked about geometric effects like this, the center of rotation is also always going to be origin in such cases, right? And you can see that see that as well here. 0 is the center of rotation. It goes like this, but there's another thing happening as well. We'll talk about that with origin as the center. Like, that's one thing that's happening. But you see, the magnitudes were also changing. Magnitudes were also changing. When we multiplied by W, remember what happens to the magnitude? Magnitudes of Z1 and Z2, they get multiplied by 2, both of them. So they increase by a factor of 2. How do we describe that in transformations language? Something gets something becomes twice the distance from the origin as compared to what it was before. Enlargement, stretch. So it has something to do with the scale factor, right? With the scale factor. It's not exactly stretch, because stretch is done with respect to a line, right? Remember function transformations? When we did that, in stretch, you think of distance from a line. We are not talking about distance from a line in this case. It's distance from a point, and the point is origin. The distance from origin was 1.5 earlier. After transformation, it becomes 3. In the other case, it was 3 earlier, then it became 6. We're talking about distance from a point. That is enlargement. That is enlargement. Okay? That's enlargement. So we will say this is an enlargement. What's the scale factor of enlargement? 2. And the center of enlargement is origin. That's the second transformation that's happening here. Okay? These are two things that are happening. Magnification is not quite the correct terminology. We have to use transformation language, right? Transformations, what kind of transformations do we know about? Rotation, enlargement, reflection, translation, stretch, right? Those are the keywords that you should be using. Okay? Okay, so it has to be enlargement. That is what it is going to be precise. Sometimes in such questions, they allow other terminology as well, but that varies from marking scheme to marking scheme. Sometimes they will allow some other word. Sometimes they would not allow another word. So to be sure, to not risk it, you should always use the correct terminology, that is enlargement. Yeah, so depending on their mood in some marking scheme, they will allow something else. Sometimes they will not allow something else. You can't guess that. Okay, you can't guess that. So write the correct terminology. This is enlargement. You should write enlargement in this case. Okay. Take it. That was question number 6. Let's look at the next one. Since enlargement is not uh, explicitly part of your A-level syllabus, they may sometimes allow you to use some other terminology for this as well. But for rotation is actually not also part of your syllabus explicitly. You only had reflection, translation, and stretch. Yeah, so both of these transformations are not exactly part of your syllabus or for A levels. You are using them from O levels. So for that reason, they might give you some leeway if you describe it some other way as well. But I would not recommend that you risk it. It's better to use the actual words rotation and enlargement, and that will be safer. Okay. Question number 3 from this paper. We have two complex numbers s and t that are given like this: 5 into cos of 0.25 plus iota sine of 0.25. That's one complex number, and another complex number which is 6e raised to power 3 iota. They're saying express s over t in the form re raised to power iota theta, where argument is between these two numbers minus pi and pi, and r is greater than 0. Those are conditions that you always have to follow in any case. Let's express it in this form. Now, first of all, we can express s in re raised to power iota theta form, right? What will it look like? The modulus of this complex number is 5, and the argument is 0.25. This is the argument 0.25. This is the modulus r. The standard form in re raised to power in this exponential form looks like this: re raised to power iota theta. So we can write down this number like this: r, which is 5 into e raised to power iota theta. That will be 0.25 times iota. This is the complex number s. The complex number t is already given in this form: 6e raised to power 3 iota. What we are supposed to do is evaluate s over t. That is straightforward now. In the numerator, we've got this: e raised to power 0.25 iota. In the denominator, 6e raised to power 3 iota. That simplifies to 5 over 6. E raised to power this divided by e raised to power this. The powers are going to get subtracted, right? So we have, since the bases are the same, powers get subtracted, and we get e raised to power 0.25 iota minus 3 iota. Now you can see what that turns out to be: 5 over 6 e raised to power, what's this number? Minus 2.75 iota. Now you can check if this argument is in the interval that is given, minus 2.75. It is within that interval, right? Minus pi is minus 3.14. So this does fall in that interval. So this is your final result then. Okay. So the first part was fairly straightforward. This is all that we had to do in this. Let's look at the next one. Now they're saying in an Argand diagram with origin O, the points A and B represent the complex numbers S and S over T respectively. By considering the line segments OA and OB or otherwise, state the two geometric effects of dividing a complex number by 6e raised to power 3 iota. Okay, now let's think about this. We can make an Argand diagram, and that will make it easier to understand. Let's mark those 2 points here. We have done a similar question, I think, in another paper in June 25 as well. This is 0. This is the real axis. This is the imaginary axis. Let's mark those 2 points. One point is S. What is point S? S is 5e raised to power 0.25 iota. 0.25 is an acute angle. So it's going to be in the first quadrant. The argument is 0.25. Modulus is 5. 5 means the distance from origin is 5 units. So we mark a point that is 5 units away from the origin at an angle of 0.25. It would look something like this. This might be a point 5 units away such that its angle is 0.25. This is the point S. Okay. In fact, they're saying A and B represent S and T respectively. So we can call this point A. Okay. Acha. What about S over T now? S over T we found to be 5 over 6 e raised to power negative 2.75 iota. Now, where is this number going to be? A was 5 units away from the origin. 5 over 6, that is much closer to the origin now, right? 5 over 6 is the new modulus now. That means that its distance from the origin is 5 over 6 units. What about the angle? The angle is negative 2.75 iota. Negative 2.75, that's going to be in this third quadrant, right? So we can mark this point somewhere here. Negative 3.75. Distance should be 5 over 6. So that means this distance, whatever this was, this divided by 6. So it might be somewhere here, let's say. It should be much closer to the origin. Let's say this is the point B now. And this point is such that this distance here, how much is this? This angle here, this is negative 2.75. Now, what are the geometric effects of going from OA to OB? OA to OB. Geometrically, what transformations are happening? What transformations are happening? How do we describe them? What transformation is happening? Any ideas? How much has the angle changed? It was 0.25 earlier, and we're going in this direction, right? Whatever was the angle before, we are subtracting 3 from that. We're subtracting 3 from that. So it's a rotation. That's one thing that's happening. There's a rotation about origin. Origin is the center of rotation, and the angle of rotation is pi radians. That is one thing that is happening. We can say there is a clockwise rotation, 3 radian. 3 radian clockwise rotation about origin. That is one thing that's happening. Okay. A clockwise rotation by 3 radians with origin as the center of rotation. That is one thing that is happening. What else? Is there anything else that is changing? It's shrinking. It's becoming smaller. What transformation is that? What's the name of that transformation? So when something becomes smaller, we call that enlargement. Stretch is when only x coordinate changes or only the y coordinate changes. In this case, we're talking about distance from a point. In stretch, we talk about distance from a line. This is distance from origin, distance from a point, from a single point. Initially, the distance from origin was 5 units. Now it has become 5 over 6 units from origin. Distance from a point, that comes from enlargement. Enlargement has a center of enlargement, as you've done in O levels. The distance from origin was earlier 5. Now it has become 5 over 6 units. What's the enlargement factor? The scale factor. You are dividing by 6, right? So you can say it's an enlargement. That's the name of the transformation. It's an enlargement with scale factor. Now, since it's getting closer to the origin, or the length of this line is becoming smaller. It was OA earlier. Now it is becoming OB. The scale factor is going to be less than 1. So the scale factor in this case is 1 over 6. We are dividing by 6, so that's 1 over 6. And the center of enlargement, that is going to be at the origin. The center of enlargement at origin. Okay, they generally do not require that you necessarily write the center of rotation and center of enlargement. This is going to be acceptable if you just write enlargement with scale factor 1 over 6 here and 3 radian clockwise rotation. But this will be the complete description then if you also write the center of rotation and the center of enlargement. Yes, Meetup. So in complex numbers, when you go from one point to another, there are two things that are changing, right? One thing that's going to change is modulus, and the other thing that's going to change is argument. That is, if you have the complex number in this form, re raised to power iota theta form, in this case, one thing that is going to change is modulus, that means enlargement. The other thing that's going to change is argument, that will mean some kind of rotation. You will also see other kinds of transformations in complex numbers, reflection in particular, and that comes with conjugates of complex numbers. So they will sometimes give you a complex number like this, 3 plus 4 iota, and then say the conjugate of that is 3 minus 4 iota, or you can figure this out yourself. What's the geometric relation between these two numbers? 3 plus 4 iota and 3 minus 4 iota? If you think of an Argand diagram, if one number is here, the other number is going to be below here, right? Because its imaginary part is negative of that. This is a reflection in x-axis. That can also happen sometimes. Reflection in x-axis. Okay, in this case, prepositions are really important. So if you say reflection along x-axis or on x-axis, you can lose marks. You either write that it's a reflection with x-axis as the line of reflection. That will be very easy to understand then without any ambiguity. But if you want to write it in 2, 3 words, you would say reflection in x-axis. Do not use any other preposition. Okay? Asked about it, maybe a couple. Okay, this is the next one that most people have problem. And now again, complex numbers, question number 5 from this paper. Let's do this. The diagram shows the locus of points representing the complex number z satisfying this equation. For the points on this locus, determine the maximum and the minimum possible values of modulus of z. We are given the equation of this circle. Remember equation of circle in complex numbers form? What's the standard form for that? It's this, right? Z minus something, modulus of that, that is equal to R. That's the standard form for equation of a circle on an Argand diagram. Z minus some point equals radius. Now, first of all, let's convert it to that form. Convert it to the standard form with minus common outside. It will look like this, modulus of Z minus 5 plus 4 iota, that is equal to 3. And now we know the radius of this circle is negative 5 plus 4 iota, and the radius is 3. You can mark that there now. This is the center of the circle. Center is minus 5 and 4. That's one thing that we know about. And the radius is 3. Now what we're looking for is determine the maximum and minimum possible values of modulus of z. How do you figure this out? Modulus of z means distance from origin. Distance from origin. So starting from the origin, given that z can be anywhere on the circumference of the circle, what's the greatest distance that you can have from the origin? Let's try to figure that out. Starting from origin, what's the closest point? What's the closest point to the origin? Is this the closest point on the circumference? It's not. We can keep getting closer and closer. It will be somewhere around here. Now, what exactly is this point going to be? This will be the point that we get if we were to join the origin with the center of the circle. The point where this line crosses the circumference, this is the point from which the distance of origin is going to be the shortest. OX, this is the shortest distance. And then what about the greatest possible distance, maximum possible distance? Maximum possible distance would be if you were to go to the other side of the circle, passing through the center of the circle. This distance from the origin to this point, let's call this point something, let's call this point y. OY is going to be the greatest distance from origin, greatest possible distance from origin. We need to find these two values, OX and OY. Now, how can we find them? We know that the radius of the circle is 3. So we know this distance is 3 units. This is also 3 units. We know the point O, that's origin. Center is negative 5, 4. Let's call that something as well. Center is C, let's say. We can find the distance OC first of all. Let's find the distance OC, origin to the center, and see what this turns out to be. Use the distance formula. Minus 5 minus 0 whole squared plus 4 minus 0 whole squared. And that will give you 25 plus 16, which is square root of 41. That's the distance OC. Once we've got the distance OC, what about distance OX? That will be the least possible value of modulus of Z. It will be OX, right? This distance. This will be the shortest distance from the origin. This will equal square root of 41. That's the distance from origin to the point C minus this radius. So this minus 3. That's the least possible value of modulus of Z. And then the maximum possible value. This is the minimum. Then they said maximum value of modulus of Z. We also have to find that. Maximum value turns out to be OY, which is going to be square root of 41 plus 3. That's the maximum value. If they wanted exact answers, you could leave it as it is. In this case, they have not specified exact or decimals. You can write decimals as well. That's also fine. Square root of 41 minus 3, and that gives us 3.40 to 3 significant figures. And then the other one, that gives us 9.40 to 3 significant figures. That's the least value of modulus and the greatest value of modulus. Make sense to everyone? Okay. All right, let's move on to part B. It says, for the points on this locus, determine the minimum possible value of argument of Z. Minimum possible value of argument of Z. Now, where is the argument going to be minimum? Remember where argument is measured from? From this positive real axis. That's where we measure argument from. Now, let's start from there. For points on this circumference, where is the least argument going to be? Where is the least argument going to be? Yes, where is the least value of argument going to be? Least value of argument. Now, this is 0 angle. We can keep going on, keep going on. Where is the first time we touch the circumference? This point here. This is where the argument is going to be least. Not on the other side, because remember, we are measuring angle from the positive real axis. So the angle is increasing in this direction. So the first time we touch the circle, that will be a tangent at this point. This is where the argument is going to be least. We are looking for this particular angle. That will be the least argument. Okay. Now, how do you find this angle? Whenever we have a tangent to a circle, remember, we have this property, tangent and radius, they are perpendicular to each other. So we can make a triangle like this, join that point with the center of the circle. You get a right angle triangle like this. It's a right angle triangle. Do we know anything about this right angle triangle? We know. Do we know any sides? Yeah. So we know this side is 3, right? And we also know this side. We have found that in the first part, square root of 41 from O to C. This side is square root of 41. We know these two sides of this right angle triangle. Using that, what we can do now is we can figure out this angle. Achha, if we can find this angle, is that going to help? Then we can find this angle as well and subtract that from pi. Okay, so that's the plan. That's what I'm thinking. What we can do first is we can find this angle inside the right angle triangle. Let me highlight that. So focus on this triangle, this right triangle. We can find the angle inside this triangle, this one. Once we've got that, we could also find the angle outside here. Because we know this point, this is -5 and 4. We can find that point as well, that angle as well. And then we could say angle on a straight line is pi, subtract from pi this angle inside the right triangle and this angle, and you'll get that argument that you're looking for. Okay, let's start with the triangle first of all. Again, I'll call this point something as well, so we can refer to that in our working. This point where the tangent is touching the circle, I'll call this point Z. So the triangle OCZ, let's focus on that. In that triangle, with respect to this angle, let's call this angle θ1. With respect to θ1, square root of 41 is hypotenuse, 3 is perpendicular. Which ratio do we use? 3 is opposite. Square root of 41 is hypotenuse. That's sine. Sine of θ1, that equals 3 over square root of 41. And that will give you the value for θ1. You can see what that is. What's the value of θ1? What's the value of θ1 that we get? Make sure your calculator is in radian mode for this. This is one thing that we wanted to find out. 0.4876. Okay, thank you. Do not round off the values yet. Do not round off the values. You'll get wrong answers at the end. 0.4876. Okay. Now this is one angle. We could also find this angle outside. This is θ2. How do you find this now? We could make another right triangle outside the circle like this. This is a right angle triangle. For this right angle triangle, we know the base. The base is 5 units because the x coordinate here is -5. The height is 4 units. So we know opposite, we know adjacent, and we also know the hypotenuse. We can use sine, cos, tan, any of them, and they will work. If we use tan, we could say tan θ2, that equals 4 over 5. That will give you the value of θ2. You can see what that is. What's the value of θ2? 0.6747. 0.6747. That's the other angle. And now to find that least argument, this is what we were looking for. We can say angle on a straight line is pi, subtract from pi θ1 and θ2, and that will be your final answer. Let's do that. This is the value for θ2. Now they were asking for the minimum possible value of argument of z. That will be pi minus 0.4876 minus 0.6747, and that will give you the final result. You can see what that is. 1.979. Round it off to 3 significant figures now. This is your final answer, and that will be 1.98. This is the minimum value for argument of C. Any issues with this? Okay. This was also not that difficult. If you know your arc diagrams well and the notations well, this was a fairly straightforward one as well. 4. Let's move on to this. It's given that Z1 is equal to R1 e raised to power iota theta 1 and Z2 is equal to R2 e raised to power iota theta 2. Show that conjugate of this is equal to Z1 conjugate into Z2 conjugate. How do we think about this now? Conjugate of these two numbers, they're saying they're equal. Now, first of all, let's evaluate. Now, they've not really told you what this stands for. In past papers, generally, if you look at the pattern, whenever they use this notation, they tell you that it means conjugate, right? But in this case, in this question, they have not really mentioned that. So you need to remember this, that this asterisk stands for conjugate, okay? Achha. Now, how do we show this? Let's start with the left-hand side. On the left side, you've got z1, z2, and then whole conjugate. Can we evaluate z1 into z2 first of all? Let's see what that turns out to be. Let's multiply these two. Z1 into z2. What would that be? R1 into R2, they get multiplied. Let me actually show one more step. R1 iota theta 1 times R2 e raised to power iota theta 2, right? That is what it will become. Now R1 and R2, they get multiplied, so you get R1 into R2 e raised to power iota theta 1, e raised to power iota theta 2. The powers get added and it becomes iota theta 1 plus iota theta 2. That is what we end up getting for z1, z2. Okay. Now, what about the conjugate of this number? What about the conjugate of this number? Can we write down the conjugate of this somehow? What's the conjugate going to be? Any idea? How do we write down the conjugate in this form? We know what conjugate is in x plus y iota form, right? So for example, if we have z equal to x plus y iota, then conjugate of z, that is given by x minus y iota. If you think of it graphically, if you have a point here, for instance, if this is z, that means this is x coordinate, this is y coordinate, this is the real part, this is imaginary part. When you take conjugate of that, what happens to x? X remains the same, y becomes negative, right? That's all that changes. So z conjugate goes here in this place. That is where z conjugate goes, right? It goes to negative y. Now, if you think of modulus and argument, how do they change? How do modulus and argument change in this case? What's the modulus of z and what's the modulus of z conjugate? They're going to be equal to each other, right? Whatever is the modulus of z, it will be the same for z conjugate. So we could say z1 into z2 conjugate of this, that is going to have the same modulus, this number that is multiplying outside, that will remain the same, r1, r2. That is not going to change. Acha, now, what about the argument? What about the argument? Whatever was the argument for the original complex number, conjugate is basically a reflection of that in the x-axis, in the real axis. That will become negative. So now that is negative theta. So the argument basically just becomes negative. Argument becomes negative. So whatever was the argument here, which was theta 1 plus theta 2, now we could put a negative sign with that. We could say it will become minus iota theta 1 minus iota theta 2. That is what z1 into z2 whole conjugate is. Does that make sense to everyone? Right? Michelle, what's the problem? We have this complex number z. We have this complex number z. Where is its conjugate going to be? Where is its conjugate going to be? Its conjugate is going to be with the same real part, but the imaginary part will become negative. Real part will remain the same. Imaginary part will become negative. So it's going to go down there, right? Now, what changes about its argument and modulus when it goes there? So for example, if the modulus was 3 earlier, what about the modulus of conjugate? That still remains the same. That is not going to change. Modulus is not going to change. But what about the argument? What happens to the argument? If this angle was, for example, pi over 6 earlier, now when this point goes down there, the argument becomes negative pi over 6. So the argument just becomes negative. That's the only thing that changes. So in r e raised to power iota theta form, when we find conjugate, the argument becomes negative. In x plus y iota form, imaginary part becomes negative. In r e raised to power iota theta form, you could say z conjugate is r e raised to power negative iota theta. Does that make sense? Okay. That's what the argument becomes. Now, that's exactly what we're doing here. So in the previous case, the argument was theta 1 plus theta 2. If I take iota common outside, the argument inside remains theta 1 plus theta 2. All we're doing is, with this whole argument, this whole thing is the argument, right? We are putting a negative sign with the whole thing. So you could say minus iota into theta 1 plus theta 2. We're just putting a negative sign with the whole thing. And if you were to simplify that, that negative will come with both of them, right? With both theta 1 and theta 2. Okay, now that's the left side evaluated. What about the right side? Do the same thing on that as well. Evaluate both of them, Z1 and Z2, using the same logic now that you understand what the conjugate is in this form. You can say Z1 conjugate. What is that? Z1 conjugate is going to be R1 e raised to power negative iota theta 1. What about Z2 conjugate? That will be R2 e raised to power negative iota theta 2. You just multiply both of them. That's what they're doing here. Z1 conjugate times Z2 conjugate. See what that turns out to be. Z1 conjugate into Z2 conjugate. Multiply both of them. You get R1 e raised to power negative iota theta 1 times R2 e raised to power negative iota theta 2. R1 and R2, they get multiplied. Powers get added and you get minus iota into theta 1 plus theta 2 from this as well. And they're both the same. That is what we had to show. Right? They're both the same. Any issues with this? Okay, so you can say, therefore, they're both equal to each other. Z1, Z2 whole conjugate. That equals Z1 conjugate into Z2 conjugate. That is what we end up getting from this. All right, let's move on. Now they're saying z equals this is a root of this equation where b and c are real. State the other root and hence find the values of b and c. Can we state the other root if we know one root? It's a polynomial where b and c are real coefficients. What's the property of polynomials? If any polynomial has any complex solutions, they always occur in conjugate pairs. As long as the coefficients are real, they're going to appear in conjugate pairs. Now, if one root is 3e raised to power pi over 4 iota, what's the other root going to be? What's the other root going to be? Anyone? What's the other root? Conjugate of this. What's the conjugate of this number? 3e raised to power negative pi over 4 iota. Right? That's what the conjugate of this number is going to be. We just put a negative sign with the argument using the same logic that we saw above. Now they're saying find the values of b and c. If these two are solutions of this equation, we can see how we can find the values of b and c. Now, input both of them there and try to solve the equation. Let's see if we can do that. Let me think about an efficient way of doing this. If we do it directly, we would have a square there. We can evaluate the square and then convert it to that form. Okay, let's just input in that equation. Now, there are two ways of doing this. One idea is that you first convert it to x plus y iota form, both of them, and then you input them in this equation. That is one idea. Or, yeah, I think the quickest way is probably going to be this. So let me do it this way. What I'll do is I'll convert both of them to x plus y iota form. Okay. Let's convert both of them to x plus y iota form and see what we get from that. If we convert both of them to x plus y iota form, how do we do that? Modulus is 3, right? And argument for the first one is pi over 4. So we can first write it as the first root as 3 into cos of pi over 4 plus iota sine of pi over 4. Simplify this, put this on your calculator, and that will give you 3 into under root 2 over 2 plus iota under root 2 over 2. This is what we end up getting from this. This is our first solution. Okay. What about the other one? Let's convert that to that form as well. In this case as well, the modulus is the same, just the argument is now negative pi over 4. So we can say 3 into cos of negative pi over 4 plus iota sine of negative pi over 4. Put this on your calculator and that will give you 3 into cos negative pi over 4. I think that is also going to be under root 2 over 2. Sine of negative pi over 4, put that on your calculator, you'll get negative under root 2 over 2. Now, these are two solutions that you're getting. Now, one idea is that you make factors from this. Make factors from this and see what those factors turn out to be. What are the factors going to be? Z minus 3 under root 2 over 2 minus 3 under root 2 over 2 iota. That is one factor. The other factor from there turns out to be 3 minus under root 2 over 2 plus 3 under root 2 over 2 iota. This is the other factor. We can find the quadratic factor, which will be this thing, by multiplying both of them, right? Like we used to do when we had one complex root given and we had to find the other roots. So it's basically a similar process that we are given the solution. This is the solution. These are the solutions. You find factors from them and now you can multiply both of them and that will give you an equation of this form. Let's multiply both of them. Where did that go? Now, how do we multiply them? You can think of it like this. These are linear factors. Let me write that down here. You could think of this thing as A and this is B. So this is A minus B. This is A and this is B. This is A plus B. A minus B into A plus B, that becomes A squared minus B squared. So this will simplify to Z minus 3 under root 2 over 2 whole squared minus B squared, which is 3 under root 2 over 2 whole squared. There's an iota here as well. This is what we end up getting. Now we can simplify this and see what that gives us. Let me do it on the right side here. It becomes z squared minus 2 into this into z. What will that be? Minus 3 under root 2 times z plus square of this number. What will that be? Square of this number? 9 into 2 over 4. 9 over 2. This is a squared minus 2ab plus b squared. I'll just confirm that as well. Or has anyone confirmed that? Is that what you get? 3 under root 2 divided by 2. If we square this whole thing, this gives us 9 over 2. Okay. Then we've got the same thing here as well. So we have minus 9 over 2. That's the square of this thing. But then iota squared, that will also become negative 1. Simplify this further. And that gives us z squared minus 3 under root 2 times z plus 9. So what are the values of b and c then? The value for b, that's the second term, that turns out to be negative 3 under root 2, and the value of c, the constant term, that turns out to be 9. That is what we were looking for. B is minus 3 under root 2 and c is equal to 9. Okay, makes sense, right? You can also use sum of roots and product of roots. That will also work. You can root sum of roots and product of roots as well. We do that as an alternative method. So those of you who know that method, sum of roots, product of roots, that will be slightly more efficient. You can definitely use that. That is allowed. Okay. This one is what is explicitly part of your syllabus. So you need to know this method. That's an alternative method that's not required by the syllabus, but is allowed, of course, as long as you're showing working for that. If you know that, that will also be correct. As long as you're doing everything correctly, that's perfectly okay. Okay? Both are valid. Both are valid. This is a general method that will work in every case. The other sum of roots and product of roots method, that does become slightly complicated if you have too many unknowns. But this will always work, right? This method will always work, although it might be a bit lengthy in some cases. How do you find conjugate when it's in the form r cos theta plus iota sine theta? In that case, it's the same. So if you have z equals r into cos theta plus iota sine theta, this is very similar to x plus y iota form. The first part is real and the second part is imaginary. So its conjugate is just going to be r cos theta minus iota sine theta. We just put a negative sign with the imaginary part. But in r e raised to power iota theta form, in that form we put the negative with the argument. Is this okay to everyone? How many, can I have raise of hands from those of you who know the sum of roots and product of roots formulas? So I can see if I should tell you that alternative method in this case as well. How many of you know the sum of roots and product of roots formulas? Okay, if you know those formulas, sum of roots and product of roots, an alternative way of doing the same problem could be, until this point, you do the same thing. You convert it to real and imaginary parts. X plus y iota form, you convert it to this form. From this point onward, you could use this alternative method. Sum of roots for this equation is given by minus b over a. So that will be minus b over 1 in this case. That's the sum of roots, which will just be minus b. So sum of roots is equal to minus b. Once you get to this point, you have the two roots. Just add both of them up. Since they are conjugates, what will happen would be the imaginary parts, they would get cancelled out and you would just be left with the real parts. Let's try that here. It will become 3 under root 2 over 2 plus 3 under root 2 over 2 iota plus 3 under root 2 over 2 minus 3 under root 2 over 2 iota. When you add both of those roots, the result should equal negative b. Now what happens is these two get cancelled and you're just left with 3 under root 2 that equals minus b. So the value of b turns out to be minus 3 under root 2. So you can find the value of b like this. And similarly, product of roots, what is that given by? Product of roots of a quadratic, that is c over a. So the last term divided by the first term. So the product of roots is actually just equal to c in this case, c over 1, which is just c. So you could multiply those two roots, and then the product should equal C. In this case, multiplication is actually going to be more efficient if you do it in the original form, right? Multiplication is more efficient in r e raised to power iota theta form. So you could use that form directly in this case, and you'll get 3e raised to power iota pi over 4, or you can say pi over 4 iota. This multiplied by 3e raised to power minus pi over 4 iota, that equals c. 3 into 3 is 9. Powers get added, pi over 4 iota minus pi over 4 iota. The power becomes 0, and we're left with just 9. So 9 equals c. That's the value of c that we end up getting. Okay, that's an alternative method. If you know how to do that, you could do it like this as well. Yes, let's move on. That was part B. Question number 6. Now we've got complex numbers again, but it's very similar to another question that we did, I think, in the previous class as well. It's very similar to that. We have a fraction, and they're saying this fraction is real. That means the imaginary part of this fraction is supposed to be 0. So we simplify this fraction first of all, but before that we need to put z equal to x plus y iota. Let's do that. Let's start with that. So we can separate out the real part and the imaginary part. Let z be x plus y iota. Then that fraction can be written as z plus 4 over z plus 4 iota. This can be written as x plus y iota plus 4 divided by x plus y iota plus 4 iota. Now multiply and divide by the conjugate of the denominator. So you multiply and divide by x minus y iota minus 4 iota, right? You just change the sign of the imaginary part. In the denominator as well, you've got this. Simplify the numerator. X into x is x squared. X into minus y iota is minus xy iota. X into minus 4 iota is minus 4x iota. Now 4 iota into all of those terms, y iota into all of those terms, that will give you xy iota minus y squared iota squared minus 4y iota squared. Now multiply 4 with all of those terms. 4x minus 4y iota minus 16 iota, whole divided by the denominator. This is a plus b into a minus b, right? X is a, so you can say x squared minus b squared. This whole thing can be considered as b, right? So minus y iota plus 4 iota whole squared. You can do normal multiplication as well. That will also be fine. That's your choice. If you want to do multiplication directly like we did in the numerator. Now simplify this a little. The denominator is irrelevant because when we input it equal to 0 eventually, that is going to get eliminated in any case, right? So let's keep the denominator as it is. Let's just simplify the numerator. What do we have in the numerator now? Let's write the real terms together. Real terms are x squared plus 4x. These are the terms that do not have iota, but then iota squared terms, they're also going to be real. Iota squared is negative 1, so this term is going to become plus y squared. We've got iota squared here as well. This is going to become plus 4y. These are all the terms that are real. Okay, what about imaginary terms now? These two imaginary terms are the same, so we've got some cancellation happening here. And then the others are all different. Okay, so the remaining terms are minus 4x iota minus 4y iota minus 16 iota. These are the terms that are imaginary. The denominator, we can split the denominator, right? Write the real part separate, imaginary part separate. The real part is this over x squared minus y iota plus 4 iota whole squared, and this divided by x squared minus y iota plus 4 iota whole squared. Now this is the imaginary part. Since they're saying this fraction is real, that means this whole thing, this must be equal to 0. So you equate it to 0. Equate this imaginary part to 0. In the numerator, you have minus 4x minus 4y minus 16. That's the imaginary part, right? Divided by whatever this is, x squared minus y iota plus 4 iota whole squared. Put this equal to 0. This goes to the other side, gets eliminated. Iota also gets eliminated. And we're just left with minus 4x minus 4y minus 16 equal to 0. That's an equation that we've got. We can divide by negative 4, and the equation would become x plus y plus 4 equal to 0. This is one equation connecting x and y that we've got. We need one more equation to be able to find the values of x and y. Modulus of z is square root of 10. From that we can get another equation. If modulus of z is equal to square root of 10, that means square root of x squared plus y squared, that is supposed to equal square root of 10, and that gives us x squared plus y squared equals 10. Now you solve these two equations simultaneously. From the second equation, for example, I can say y equals minus x minus 4. Put that in the first equation and that will become x squared plus minus x minus 4 whole squared, that equals 10. X squared plus x squared plus 8x plus 16, and then minus 10 from the other side. This simplifies to 2x squared plus 8x plus 6 equal to 0. X squared plus 4x plus 3 equal to 0. Can we factorize this? When you factorize this, I think you're going to get x squared plus 3x plus x. That will give you x squared x plus 3 into x plus 1. That will be the factorized form that you end up getting. And then x equals negative 3 or x equals negative 1 from here. We're getting multiple values. Are both of them possible? Okay, so they're saying find the complex numbers z. So there are multiple possible answers. So we consider both of these x values, put them there. You put x equal to negative 3 and you put x equal to negative 1. The corresponding y values, they turn out to be minus into minus 3 minus 4, which is minus 1 here. And the other one turns out to be y equals minus into minus 1 minus 4, which is y equals minus 3. Right? So what are the possible values of that number z? Z could be minus 3 minus iota, or z could be minus 1 minus 3 iota. These are the two possible values of z that we end up getting from this. Second question, let's move on to the next one. Now they're saying it's a complex number question, right? We've got an Argand diagram given. The shaded region on the Argand diagram shows points representing complex numbers z defined by two inequalities. The shaded region is bounded by a circle and a line parallel to the real axis. Real axis is the horizontal axis, right? We've got this line. The boundaries of the region are included in the shaded region. That means this line is included and this curve is also included. So you'll have greater than equal to or less than equal to signs in the inequalities, right? You'll also have the equal to signs. Find two inequalities in terms of z that define the shaded region. Now, how do we think about this? One inequality would be, so one line that is the boundary of the shaded region is this orange line. How do you describe this line? It's a horizontal line, right? What's the equation that we've got for horizontal lines? Y equal to something, right? Y equal to some constant. On the vertical axis, we have the imaginary part of the number. So we could say imaginary part of z that equal to something, that equal to what? This number is negative 1. So imaginary part of z equal to negative 1, that will be the equation of this line, this horizontal line that we've got. So what would the inequality be? we need to be below this line, right? So the inequality that we get from that, that is going to be that the imaginary part of z that is less than or equal to -1. That's one inequality that we get. Now, what about the curved part? What about the curved part? This curved part? How do you describe this? This is arc of a circle. So you are inside the circle. You're inside this circle. What's the equation of the circle? Remember, we need to know what the format of equation of a circle is in complex numbers as well, right? On Argand diagram, equation of a circle, the standard form for that is written like this. Z minus something that equals R. That's the form that we've got for equation of a circle, in which this point represents the center of the circle and this represents the radius of the circle. Okay. So what will be the equation of the circle then? The center is this point. This point is -2 plus iota. So you would say modulus of z minus -2 plus iota. The equation of the circle would be equal to this thing equal to the radius. What's the radius? 1, 2, 3, 3 units equal to 3. That's the equation of the circle. Now you have to be inside the circle. Since you are inside the circle, since you are inside the circle, what that means is the distance from the center needs to be less than 3. So rather than the equal to sign, you would put less than or equal to 3. And that's the second inequality that we've got. You can leave it like this if you want. You can also simplify this to z plus 2 minus iota. Modulus of that, that's less than or equal to 3. That's the second inequality. Okay. Now, can we write it as imaginary part of z less than or equal to negative iota? No, you cannot do that. When we say imaginary part of z, iota is understood in that. Okay, it's understood that it has iota with it. We would just use numbers in inequalities and equations. We are not going to have iota on this side because this means the distance imaginary part of z is less than or equal to negative iota. Iota term is already incorporated in imaginary part. So that's the convention that we don't use this. However, since in this question, in the diagram that they've given, they've used negative iota, -2 iota. They might have allowed this in the marking scheme as well, but the convention is that we use less than or equal to -1. As in, we just use we just use the number without the iota. Okay? Makes sense, right? Let's move on to the next one. Find the greatest value of modulus of z for points in this region. Greatest value of modulus of z. Modulus of z, what does that represent? Modulus of z. Modulus of z means maximum distance, or modulus of z just means distance from origin, and then greatest would mean maximum distance from origin. Modulus of z means distance from origin. Now, for points in the region, where are you the maximum distance from the origin? So let's start from the origin. This is the origin. Now, how far can you go in the shaded region? On the extreme left, right? This point here somewhere. This point is going to be the furthest from the origin. So what we are looking for is the length of this green line. We need to find the length of this green line somehow. That will be the maximum distance from the origin. Okay. Now the question is, how do you find this length? How do you find this length? Now, what information do we have? We have the vertical length here. This is 1 unit. How are we sure it's the green line? as in just by looking at it. Let me actually set this background so it becomes easier. So from the origin, if you go here, for instance, this is 2 squared plus 2 squared. That's 8, square root of 8, right? When you go here, you already are 4 units on the left side. That's like 4 squared, 16 squared. So the minimum distance that you've got here is 1 this, 4 this minimum. It's more than 4. So that will be at least square root of 17. At the bottom, this is square root of 8. So the greatest distance would be on the extreme left. Okay. Now there's no set method for this. You just have to look at the diagram and see, okay, what point looks furthest away from the origin. So that's the point that's furthest away from the origin. So we're looking for that distance now, the green distance. Okay. Now the question is, how do you find this greatest distance? How do we find this greatest distance? Now, it doesn't look very obvious in this case to me right now, because we just have this length, one length, this is known, and we don't really have a lot of other information here for now. We could possibly make an equation like this, make a triangle like this. That might help because we know this side, and we could find this angle somehow. We know the other side as well. That's the radius. This radius is 3 units. That side is also known, and we've got that one angle. Do we have this angle somehow? Do we have this angle? Do we have this angle? No, we don't have this angle. Okay. So the way to do these questions is generally what happens is something using trigonometry and making triangles is going to work. If you cannot figure out something directly, for questions involving circles, it's a good idea to use the coordinate geometry methods that you've done in P1 as well. Now, what do I mean by that? We don't know what this point is, right? If we could somehow find this point, then finding this distance is pretty straightforward, right? Distance between 2 points. Now, using coordinate geometry methods, is there a way to find what this point is? Can you find this point somehow? We could solve the circle. We could write down the equation of the circle and then just input -1 as the value of y in that. And that will give us that point's coordinates. Now, let me write down the equation of the circle. What's the equation of the circle going to be? The center has coordinates. Let me write that down here. The center has coordinates -2 and 1. These are the coordinates of the center. Radius is 3. Can we write down the equation of the circle in coordinate geometry form? What would that be? X minus a whole squared. That means x minus -2, which becomes x plus 2 whole squared, plus y minus 1 whole squared equals 3 squared. That will be the equation of the circle. Once we have this equation of circle, all we have to do is, we know the y coordinate of this point is -1. Input the y coordinate -1 and that will give you the x coordinate at this point. So the y coordinate is -1. Put y equal to -1 in this. X plus 2 whole squared plus -1 minus 1 whole squared equals 9. Now it takes a few steps, but it's going to be very easy to work with in problems involving circles where you have to find this point. You just write down the equation of the circle and then solve it simultaneously with a line to find that point. In this case, we end up getting x plus 2 whole squared plus 4 equal to 9. This goes to the other side. It becomes x plus 2 whole squared equal to 5. Take square root on both sides. And that will give you x plus 2 equal to plus minus square root of 5. You'll get one result from plus under root 5, another result from minus under root 5. Let's see what they turn out to be. when -2 goes to the other side, one possibility is that you have under root 5 -2. That's one possibility. We want an answer in decimals, right? So that's okay, 0.2361. Another value of x that we get will be with the negative sign. And that turns out to be negative under root 5 -2, which is negative 4.236. Now, which one of this is relevant for us? The x coordinate is negative here. So the minus 4.2361. So that means we now know this point that we had here. Let's call this something. Let's call this point x maybe. What are the coordinates of that point x now? The coordinates of the point x therefore are negative 4.236 and the y coordinate that was negative 1. So we've got that point. All we have to do now is find the distance from the origin. Use the distance formula, distance OX. What does that turn out to be? Square root of this minus 0 whole squared minus 4.236 minus 0 whole squared plus -1 minus 0 whole squared, and then take square root of that, and that will give you something. You can see what this turns out to be. This number, square of that, plus 1 squared, square root of this thing, and that is giving me 4.3525. Round it off to three significant figures, and that is 4.35. We can say the greatest possible value of modulus of z that is equal to 4.35. That is what we were looking for. Does that make sense? This is an idea that you'll have to use a lot in problems involving Argand diagrams and circles when you're looking for greatest distance or least distance. If you want to find this point, you would write down the equation of the circle in coordinate geometry form and then solve it simultaneously with some equation. In this case, we knew that y was equal to -1, so we just input y equal to -1 in this to find the corresponding x coordinate. Does this make sense to everyone? Right? What will be least? You're saying what will be the least distance from the origin? It will be this point exactly below this. This is the closest point, right? Shortest distance from a point to a line, that is always perpendicular distance. So from origin to this region, we could say the shortest distance is when you have a perpendicular to this line on top. So it will be just 1 unit here. This will be the least, if that's what you're asking about.